So good morning, dear friends. So this is a continuation of the video on carbohydrates, which comes under the topic of bioorganic chemistry. So today, what we will see is we will look at the classification of carbohydrates and another very small minor topic, which is your DL notations of how we have to label the sugars. So we label them as D-glucose, or we label them as L-glucose, or we label them as D-fructose, or we label them as L-fructose. So why? What is the reason for labeling the names as such? So that we will look into today. Okay. So if we are going down as far as this the classification. So what is the classification? So we are going to classify the sugars. The first means of classification by means of hydrolysis. So we take a sugar and we start hydrolyzing the sugar. So the sugar hydrolyzes into simple sugars. So if a sugar cannot be hydrolyzed any further, that is by acid hydrolysis or by base hydrolysis, if a sugar does not hydrolyze or break down into simpler sugar on hydrolysis, then it is called as simple sugar. If we are going to hydrolyze a sugar molecule and it breaks into two simple sugars, then it is called as a disaccharide. And if you're going to hydrolyze a sugar molecule and it is going to hydrolyze into three sugar molecules, then it is going to be called as a trisaccharide. Okay, so simple carbohydrates are called as the sugars which do not hydrolyze further into simpler sugars. These molecules are called as what? Simple sugars. Okay. Now, examples can be, glucose and fructose. And in the case of disaccharides, you can take the case of, sucrose, where it is hydrolyzed. If the sugar molecule is hydrolyzed, it gives two sugars. That is, it will give you a D-glucose and it will give you a D-fructose molecule. So it on hydrolysis, it is giving you two molecules. So it is called as a disaccharide. Okay, I hope you are able to understand, since we already dealt with linking of sugars and the cyclic structures. I feel it is going to come more simpler to you. Okay, so the third means of expressing is what we call as oligosaccharides. So if you're going to hydrolyze a sugar molecule and it breaks down to 3 to 10 sugar molecules, that is trisaccharides, tetrasaccharides, pentasaccharides, all these molecules. So if it is going to hydrolyze into these molecules, then we call the entire combination oligosaccharides. So few sugars that are going to come out, so we call them as oligosaccharides. If on hydrolysis we are going to yield n number of simple sugars, then we are going to call them as polysaccharides. So you can see the reaction here, polysaccharides on hydrolysis is going to give you what n number of monosaccharides. Okay, now let's come up, here. So let's come up here. Maybe we'll go back there later. Now, another means of classification is as aldoses and as ketosis. Please take notes. Please don't simply watch on the screen and let things go by. Unless you write, that's what I say. Unless you write, you'll be missing things. Okay. Now here you have an aldehyde group, and here you have a keto group. So the sugars can further be classified as second means of classification in terms of their functional groups, that is aldoses and ketosis. So all those sugars that are going to have aldehyde groups are classified as aldoses, and all those sugars that are going to have keto groups are called as ketosis. Now let's take another example. Now if we are going to look at this particular structure here, so let's see this rhabidose. So I expect this to be my anomeric carbon. This is 1, 2, 3, 4 and 5. There are only 5 carbons here. And if I'm going to take my glucose, there are 6 carbons here. No, based on the number of carbons, now I call ribose as a pentose. So the classification is based on the number of carbons that are present in the sugar. So I call ribose as a pentose sugar, and I call glucose as a hexose sugar because it has 6 carbons in it. So this is the third means of classifying your sugars. Okay, so I hope you understand what is going on. Okay, now Another means of classifying Another means of classifying your carbohydrates is in terms of reducing agents. So if you're going to use a reducing agent such as tolerance reagent or Fehling solution, and if the sugar is going to be reduced by tolerance reagent or Fehling solution, then it is called as a reducing sugar. So that is, the tolerance reagent gets reduced and the sugar gets oxidized. So those sugars that reduce tolerance reagent and those sugars that reduce filling solution are called as reducing sugars. So further on, in the next few videos, when we'll be going into the reactions of glucose and fructose, we will be writing the details of those reactions. Okay, so I hope you are able to understand the classification of carbohydrates. Okay, so the next topic will go into what we call as your DL notations. So here this you can mention as D and L notation. So it's not going to take very long, so we'll be finishing very soon. Okay, now have a look at this particular molecule here. Have a look at this particular molecule here. So this is your basic molecule that we call as glyceraldehyde, and it has been represented by plus. So we call it as dextrorotatory, and molecules that are having a negative sign, we can assume that they are levorotatory. And you can see that glyceraldehyde is a chiral molecule. So it is going to be like the shape of your hands. So chiral means hands. So your hands are mirror images of each other. So you cannot cut your hand to replace another molecule. That is your you cannot cut your right hand and replace it with your left hand. So that is not possible. Both are mirror images, and they have their own responsibilities and work which the other hand cannot perform. Okay, so that's why they are called as chiral molecules. Now in this DL notation, how come there is a series of molecules that are called D and there are a series of molecules that are called as L? How come? Now, suppose we take any sugar for instance, we take D-glucose. Can here. Let's see here. So I am right here. You can see here. So here. So we are taking D-glucose, and the sugar is degraded. So the sugar is degraded. Okay, so first carbon is removed as carbon dioxide, so it switches to arabinose. Again, the sugar molecule undergoes degradation. It comes to you know four carbon sugar. And then this again degrades to form a three carbon sugar. So this is a triose. The glyceraldehyde is a triose, and it is labeled as glyceraldehyde, and it has not been mentioned as a any with the os. So os, what is this os? The suffix os is generally meant for sugars. So carbohydrates, you have oses. So carbohydrates. So all the oses, OSS, OSTS, all these terminologies of these suffixes have been given for sugars alone. So that's why they are called as oses. Now here you have a polyhydroxyaldehyde, polyhydroxytops. Here, these are the two. We come back. So when a sugar is degraded and it comes, to its next stage, and it comes here, there is a Fisherman-Rosen notation. That's what we call as Fisherman-Rosen notation. Now, those sugars that are going to have, in their three-dimensional structure as per your Fisher projection, they are going to have, the OH groups, they are going to be chiral. So one half of the chiral molecule is going to be a mirror image of the other. So you can see that this is going to be a mirror image of this. This is going to face this molecule. Okay, so we have given the positive sign for the dextrorotatory and the negative sign for the lever. So all the sugar molecules, when broken down, if they come to their parent, which is plus glyceraldehyde, that is dextrorotatory glyceraldehyde, we call these sugars as D sugars. That is, in a Fisher projection, if the OH group has been represented on the right hand side, that is the last stereocenters OH group. If it is on the right hand side, that sugar is supposed to be called as the D sugar. If the stereo center of the sugar, that is, you have mentioned the most oxidized group on the top, the least oxidized group at the bottom, and the last stereo center you have the OH group on your left in the Fischer projection, then it is called as a L molecule. If you're going to have the last stereo center with a OH group on the right, it is going to be called as a D molecule. Okay, now D molecules, all naturally occurring sugars are D isomers. Okay, so most of the L isomers are unnatural or they are artificially synthesized sugars. So you can see, an example of, what I'm saying here. So if you're going to, degrade, ribulose, D-ribulose, you can see OH group is on your right. So this is fructose sugar. Okay, so the notation is D here. Here the OH group is on your left, so it is called as a L. Okay, so here again L ribulose, then you have L triose, you have D xylose and L xylose. So since the OH groups are on the left, they are called L, and on the right they are called as D. So as per Fisherman-Rosenhoff notation, in a sugar molecule with the most oxidized group on the top and the least oxidized group at the bottom, the last stereo center, the OH group is on the right, it is called as a D molecule, and the OH group is on the left, it is called as a L molecule. Okay, so I hope you understood. So if you're having any clarifications, feel free to approach me anytime. Thank you for your patient listening. And if you want more clarifications, of course, I can write it in your notebooks and explain it to you. Okay, thank you so much for your patient listening, and take care.